Westminster Bridge officially opened in 1862, replacing Thomas Page's earlier design with cast-iron arches spanning the Thames. The standard architectural histories describe conventional Victorian masonry, 7 elliptical arches, granite piers, ornamental parapets. I approached it as straightforward infrastructure documentation, cross-referencing ordnance survey sheets from the 1870s against contemporary photographs. Then I found the maintenance note, dated March 1934, archived in the Metropolitan Board of Works collection. It referenced filled conduits beneath cutwaters, sealed with concrete during routine inspections. The notation appeared nowhere in Charles Barry Jr.'s construction specifications. No drawings showed these conduits. No engineering journals mentioned their purpose. Yet renovation crews had discovered them, documented their sealing, and moved on. The Thames tidal range demands robust pier foundations, but pressure-managed voids aligned with tide gradients exceed simple structural needs. Some researchers examining similar infrastructure classify these signatures as Tartarian, inherited networks repurposed by later builders. The question remained, what function required channels the official record never acknowledged? Westminster Bridge's construction photographs from 1858 show something unexpected. The British Library holds a series of albumen prints documenting foundation work, images captioned cofferdam construction, South Pier, standard procedure for the era, timber caissons, manual excavation, masonry assembly. But examining the prints with magnification reveals marks in the exposed riverbed. Shallow grooves run perpendicular to the pier alignment, too regular for erosion, too deliberate for accident. They aligned with what would become the bridge's central span. The 1860 survey map shows no existing infrastructure at this location. The previous bridge stood 50 meters upstream. These marks suggest conduits predating the documented construction start. The official narrative credits Charles Barry Jr. with the entire design, completed over 4 years using techniques well established by mid-Victorian engineering practice. The photographs contradict this simplicity. At low tide before cofferdam installation, the riverbed shows geometric precision. The grooves maintain consistent depth, approximately 8 inches, based on comparison with visible measurement stakes in the frame. They terminate at exact intervals, matching the final pier spacing. I found similar patterns in renovation records from 1887. Workers repairing the southern cutwater noted void spaces requiring infill. The maintenance log described cavities of unknown origin within the pier structure itself. These were not expansion gaps or settlement cracks. The engineer's sketch shows deliberately formed chambers, roughly cylindrical, running vertically through the pier core. No structural engineer of the period would create such voids intentionally. They compromise bearing strength without providing access for inspection or maintenance. The Tartarian infrastructure hypothesis offers one explanation. Researchers examining pressure-managed systems in structures across Europe note similar substructures, cavities designed to regulate water movement through foundations, reducing hydraulic pressure on pier faces during tidal cycles. Such systems appear in bridges whose construction predates detailed engineering records, or where renovation documents reference removed components never mentioned in original specifications. The photograph caption remains factual: cofferdam construction, South Pier. But the riverbed beneath tells a different story, one the cofferdam would soon conceal forever. Old London Bridge, demolished between 1824 and 1831, left behind foundations that puzzled the Metropolitan Board of Works for decades. I found engineering surveys from 1867 examining the abandoned pier remnants for potential reuse. The cross-section engraving published in The Engineer shows something remarkable. The medieval piers contained internal cavities with symmetrical spacing, 8 chambers per pier, each roughly 4 feet in diameter, arranged in 2 vertical rows. The accompanying technical notation reads, "Void spaces of unclear function, possibly settling tanks or sluice channels, though no surface features suggest hydraulic application." The engineer conducting the survey, James Simpson, concluded they served no apparent purpose. Yet their symmetry exceeds medieval construction tolerances by significant margins. The chambers align vertically with less than 2 inches deviation across 40 feet of masonry. 14th century stonemasons working without precision surveying instruments could not achieve such consistency accidentally. Simpson's drawings show more. Each cavity connects to narrow channels, 6 to 8 inches wide, running laterally through the pier base. These channels do not breach the outer stone facing, they terminate within the foundation mass itself. The only explanation Simpson offered was possible drainage features, though silted and non-functional at time of survey. Some researchers examining Tartarian engineering patterns identify similar configurations in bridges across Europe, pressure equalization systems designed to manage hydraulic forces during tidal fluctuation. The closed-loop design would allow water movement within the pier without compromising structural integrity, distributing tidal stress across the foundation rather than concentrating it at pier faces. The 1867 survey recommended demolition. By 1870, the last remnants of Old London Bridge's piers had been removed. Simpson's drawings survived in the Institution of Civil Engineers archive. His notation on the final page remains factual, but troubled. Symmetry of internal features suggests intentional design, though purpose remains undetermined and unrecorded in medieval construction accounts. The piers are gone. The channels they contained and the engineering knowledge they represented disappeared with them. The Thames Embankment project, 1864 to 1870, transformed London's riverfront. Joseph Bazalgette's interceptor sewers became the visible achievement, massive brick tunnels carrying waste downstream. But the Metropolitan Board of Works maps show something else, a network of smaller conduits installed beneath the embankment's foundation, running parallel to the river, but not connected to the sewer system. I found the plans in the London Metropolitan Archives. Sheet 47, dated April 1866, labels these features as auxiliary drainage channels. Yet their placement contradicts drainage logic. True drainage follows gravity, running perpendicular to the river toward the main interceptors. These conduits run parallel, maintaining consistent elevation for hundreds of meters. The engineering notation describes them as an 8-inch diameter ceramic pipe, vitrified clay construction, installed in a gravel substrate. What troubled me was the installation sequence. Bazalgette's detailed construction logs preserved in the Institution of Civil Engineers archive show embankment foundation work beginning in January 1865. But the conduit placement drawings are dated 1864, before foundation surveys were completed, before the embankment alignment was finalized. The pipes were laid first and the embankment built around them. The conduits follow a grid pattern that predates Bazalgette's design. Where the embankment curves to accommodate existing wharves, the conduits maintain straight-line geometry, forcing foundation work to adapt around them. At 3 locations, construction logs note unexpected subsurface structures requiring route modification. The modification always accommodated the existing conduits, and they were never removed. I examined the spacing, every 40 meters precisely. The consistency suggests surveyed placement, not ad hoc drainage installation. The diameter, 8 inches, matches specifications found in Tartarian-era infrastructure studies, pressure management networks designed for gradual water distribution, not rapid drainage. Such systems appear in foundations across Europe, often discovered during renovation work, and rarely documented in original construction records. A notation on sheet 47 provides the only official explanation: existing features retained per board directive, October 1864. There is no explanation for what made them existing in soil that should have been undisturbed Thames side marsh. There is no record of who built them or when. By 1870, the embankment was complete. The conduits remained beneath, their function unacknowledged, their origins unexplained. Pont de la Concorde in Paris officially dates to 1791, rebuilt during revolutionary fervor using stone from the demolished Bastille. The French National Archives hold cadastral maps from 1810 showing the bridge's final configuration: 5 elliptical arches spanning the Seine. I overlaid these maps with the Thames embankment conduit spacing from London. The alignment matched exactly every 40 meters. 8-inch diameter specifications are noted in the margin annotations. Different rivers, different nations, identical subsurface geometry. The Paris Municipal Engineering Survey from 1856 documented foundation repairs. The report describes lateral channels within pier bases, function unknown, sealed with hydraulic cement per directive. The survey engineer, François-Marie Calais, sketched the channel configuration. Horizontal passages running through each pier's core, terminating in small chambers roughly 2 feet square. No surface features, no maintenance access, no explanation in the 1791 construction documents. Sealed. Callet's notation records that these features appear purpose-built but serve no function related to current bridge operation. He recommended sealing to prevent water infiltration and foundation compromise. The repair work proceeded. By 1858, all accessible channels were filled. Callet's drawings survive in the École des Ponts et Chaussées archive. They are precise renderings showing channel positions, dimensions, and the mysterious terminal chambers. What makes this remarkable is that the 1791 construction specifications mention no such features. The revolutionary builders documented their work extensively, itemized stone sources, labor costs, and engineering calculations. Nothing about internal pier channels, nothing about terminal chambers, yet 19th century engineers found them, measured them, and sealed them without resolving the contradiction. The pattern transcends national engineering practice. London's Thames embankment conduits were spaced at 40 meters. Paris's Pont de la Concorde pier channels were positioned at 40-meter intervals. Both systems were discovered during renovation, both absent from construction records, both sealed rather than studied. Researchers examining what they classify as Tartarian infrastructure networks note this signature. Pressure management systems installed before modern engineering documentation, rediscovered during maintenance, and systematically removed. Callet's final margin note remains understated. He concluded that the origin of internal features cannot be determined from available historical sources. The question he could not answer is this: how do two nations, building independently, replicate subsurface engineering they never documented? St. Petersburg's Neva River bridges underwent major expansion in the 1850s as part of Imperial Russia's modernization program. The Imperial Engineering journal Inženýrní žurnál published detailed plates showing foundation work for the expanded bridge piers. Plate 14, dated 1854, shows something unexpected: pressure chambers within the pier bases sized far beyond ice load requirements. The Neva's ice presents genuine challenges. Sheets 3 feet thick during severe winters can move with tremendous force during spring breakup. Victorian engineers understood this. Standard practice called for sloped cutwaters and massive pier bases to deflect ice. The plates from 1854 show both features, but they also show internal chambers, cylindrical voids 8 feet in diameter, running vertically through each pier's core. The notation in Russian reads, "Internal pressure chambers per existing foundation pattern, dimensions verified March 1854. That mention of an existing foundation pattern appears nowhere else in the construction documents. The chief engineer, Major General Konstantin Ton, never explained what he meant. The dimensions suggest something other than ice defense. 8-foot chambers provide no structural advantage against surface ice impact. They are too deep and too removed from the cutwater faces. They would, however, function effectively as pressure equalization voids, allowing subsurface water movement during freeze and thaw cycles. I found confirmation in repair records from 1891. Workers investigating foundation settlement discovered the chambers still open, lined with vitrified brick. The maintenance report noted the chambers appeared unused for their intended purpose, whatever that may have been. The engineering review recommended filling them with concrete. By 1895, all accessible chambers were sealed. The pattern matches Tartarian hydraulic engineering signatures identified by researchers examining infrastructure across the former Tartarian territories, regions labeled as Tartary on maps through the 1770s, encompassing much of Russia's European territories. The oversized chambers, the pressure management design, and the absence of explanation in Imperial Russian engineering documents are all consistent with inherited infrastructure, systems built before modern documentation practices, repurposed or simply built around by later engineers. Ton's notation offers no clarity. Existing from when and built by whom remain unanswered. The chambers that might have answered these questions are now filled with concrete, sealed beneath bridges that carry traffic across the Neva, their purpose officially classified as unknown. Charles Bridge in Prague dates to 1357, a Gothic masterpiece spanning the Vltava River. The maintenance ledger from 1878, archived at the Prague City Museum, contains an entry that disrupted my understanding. It records removal of obsolete water channels and valve mechanisms at the South Pier Foundation from August 12 to 17. The notation appears routine, standard renovation work, but obsolete implies prior use, and no medieval or Renaissance-era records mention such systems. I traced the 1878 renovation crew's work. The chief engineer, Jan Lothar, kept detailed notes. His August 15 entry describes bronze valve assemblies, heavily corroded, function unclear. He sketched 3 components: a circular valve housing roughly 12 inches in diameter, a piston mechanism with threaded adjustment, and a lateral pipe connection. The sketch shows precision machining, threaded parts, calibrated adjustment mechanisms, and high-quality bronze casting. This is not medieval technology. Lothar noted that valves were positioned at the base of the pier, 3 meters below normal water level, accessing channels that ran through the pier core. No surface controls were located, and the purpose was unknown. He recommended removal to simplify foundation maintenance. The renovation proceeded, and by August 17, all valve assemblies had been extracted and discarded. Lothar's sketches survive. The valves themselves do not. The question becomes temporal. Obsolete relative to what? Medieval construction in 1357 employed no such mechanisms. Renaissance-era modifications documented through the 16th and 17th centuries mention no hydraulic systems, yet by 1878 engineers discovered precision manufactured valves controlling water flow through internal pier channels. The valves had to predate their discovery. They had to have been installed when the bridge was built or in some earlier structure on the same site. Some researchers examining Tartarian infrastructure point to exactly this pattern: precision hydraulic systems discovered during renovations, removed rather than studied, classified as obsolete despite no historical record of their installation or use. The Tartarian hypothesis suggests these were not obsolete, but inherited, functional components of a pressure management network built before the Gothic bridge, incorporated into or left beneath later construction. Lota's final note recommended sealing foundation access points to prevent water infiltration. The channels were filled, the valves were destroyed. What remains is the sketch and the troubling question: obsolete to whom and since when? Brooklyn Bridge's foundation caissons, sunk between 1870 and 1872, represent American engineering at its most ambitious. Washington Roebling's detailed drawings show the water management systems, compressed air chambers, airlocks, pumping stations, standard technology for pneumatic caisson construction. But examining the foundation drawings at the Roebling collection in Rensselaer Polytechnic Institute, I found specifications that mirror European systems exactly. The South Pier Foundation drawing, dated June 1871, shows lateral channels running through the caisson base, 8-inch diameter, ceramic pipe spaced at regular intervals. The notation reads, "Drainage channels per established practice, specifications verified." But established where? American engineers had limited caisson experience in 1871. The pneumatic caisson method was barely a decade old. Roebling would have needed to reference European engineering journals for technical guidance. The channel spacing matches precisely 40 meters between major laterals, 8-inch diameter, vitrified clay construction. The same specifications appear in London's Thames embankment, Paris's Pont de la Concorde foundations, and St. Petersburg's Neva bridges. Identical numbers, identical materials separated by thousands of miles and multiple decades. The consistency suggests either remarkable coincidence or shared reference to some common source. I searched Roebling's archive for that source. His library inventory, preserved in his correspondence, lists engineering texts from Britain, France, and Germany, but none specifically addressing foundation drainage systems, none explaining why 8 inches became standard, why 40-meter spacing appeared optimal, why vitrified clay was specified over cheaper alternatives. The specifications appear in his drawings as given knowledge, requiring no explanation or justification. The Tartarian infrastructure hypothesis offers context. Researchers examining what they classify as Tartarian engineering patterns identify these same specifications across Europe and Asia, regions historically mapped as Tartary or Tartarian territories. The suggestion is that Roebling may have encountered these systems during his European engineering studies, documented them, and replicated them in New York without understanding their origin or full function. He followed the pattern because the pattern worked. The Brooklyn Bridge opened in 1883. The foundation channels remain presumably beneath the piers. They were never inspected, never questioned, their function assumed to be simple drainage despite their European precision. Roebling's notation provides no deeper insight, it simply says, per established practice. Established by whom, and based on what original engineering knowledge, he never recorded. Chain Bridge in Budapest, rebuilt with iron superstructure in 1849, received major modifications in 1914. The renovation photographs held at the Hungarian Museum of Science, Technology and Transport show foundation work exposing the original stone piers. Image 47 captures something unexpected: sealed arches within the pier base, filled with brick and mortar sometime after original construction. The photograph annotation identifies them as structural modifications, purpose unknown, likely 18th century. But the chain bridge was not built until 1849. The piers rest on older foundations, remnants of earlier crossings dating to Roman occupation and medieval periods. The sealed arches suggest something else: deliberate closure of spaces that once served a function. I examined the dimensions visible in the photograph. The arches span roughly 6 feet, positioned 3 meters below normal water level. Their curve follows precise geometry, semicircular, not the irregular shapes typical of foundations built around natural obstacles. Someone designed these spaces, built them into the pier structure, then at some later point, sealed them completely. The 1914 renovation report, written by Chief Engineer Arpad Zielinski, describes the discovery. Interior chambers accessed during foundation stabilization work. Chambers empty, showing no signs of use for storage or maintenance. Structural analysis indicates no load-bearing function. Recommend concrete infill to ensure pier integrity. The work proceeded. By November 1914, all accessible chambers were filled. The pattern echoes discoveries across Europe. Sealed spaces within bridge foundations, chambers that served no apparent structural purpose, features absent from construction records but present in the physical infrastructure. Researchers examining Tartarian systems identify this signature: deliberate concealment of earlier networks, spaces filled rather than documented, functions erased through systematic sealing. What required chambers at that depth? What function justified precise archways built into foundations that would spend centuries submerged? Zielinski's report offers no speculation. His engineering training provided no framework for interpreting evidence that contradicted documented construction chronology. He did what practical engineering demanded. He filled the voids and ensured structural stability. The photograph remains a single image capturing chambers that existed for unknown decades or centuries, serving unknown purposes until November 1914. After that date, they became concrete fill. The question Zielinski never asked: what happens when we systematically seal what we do not understand? Pont Alexandre III, built for the 1900 Paris Exposition, represents Belle Époque excess, gilded statuary, ornate lampposts, decorative pylons. The architectural emphasis falls entirely on surface aesthetics, but the exposition planning maps archived at the Bibliothèque Nationale show something beneath the ornament: a network of ventilation shafts concealed within the pylons themselves. Sheet 23, dated 1896, labels these features as decorative pylon bases with integrated utility access. The notation seems straightforward until cross-referenced with the actual construction. The pylons stand 17 meters tall, mounted on massive concrete bases extending 6 meters below the deck surface. The ventilation shafts run through these bases, connecting to lateral channels in the bridge foundation. The shafts are 2 feet square, far larger than necessary for simple air circulation. Construction photographs show the pylons during assembly. Image 12 captures a pylon base before decorative facing installation. The ventilation shaft is clearly visible: smooth stone lining, precise corners, metal grating at the base. The grating covers the lateral channel connection. The channel itself disappears into the foundation, running toward the river piers. No surface feature acknowledges this system. The decorative bronze work conceals everything. Why vent a bridge foundation? The official explanation noted in the construction documents claims humidity control, preventing moisture accumulation that might corrode iron structural elements. But the ventilation system connects to channels running beneath the river itself, far from any iron beams. The channels follow the familiar pattern: 8-inch diameter, 40-meter spacing, vitrified clay construction. The same specifications appear in London, Paris, St. Petersburg, New York. Some researchers examining Tartarian infrastructure point to this exact technique: utility systems masked by decorative architecture, functional networks hidden beneath aesthetic excess. The Belle Époque style provided perfect cover. Every surface ornament, every sculptural element could conceal practical infrastructure without raising questions. Ventilation becomes decoration, function disappears into art. The Pont Alexandre III remains one of Paris's most photographed bridges. Tourists admire the gilded statuary, the Art Nouveau lampposts, the allegorical sculptures. Beneath the deck, the ventilation shafts continue doing whatever they do, moving air, equalizing pressure, managing humidity, or serving some other function. The 1896 plans never quite explained. The pylons stand ornate and silent, beautiful and secretly functional. Tower Bridge, completed in 1894, presents a clear engineering narrative: hydraulic bascules, engine rooms and counterweight systems. The Hydraulic System Manual, published in 1895, documents everything: pump specifications, accumulator pressures and valve timing, standard Victorian industrial technology. But examining the manual appendix drawings, I found something unexpected. The bridge's hydraulic system integrates with older substructure, systems that predate the bridge's construction. Appendix Drawing 7 shows the hydraulic accumulator chambers, two cylindrical tanks each 40 feet deep, positioned within the bridge's southern approach foundations. The notation describes them as utilizing existing foundation voids, modified for hydraulic service. Existing from what? Tower Bridge broke ground in 1886. The site was previously open waterfront, warehouses and wharves. No earlier bridge stood at this location, yet the engineers discovered existing foundation voids suitable for conversion to hydraulic accumulators. The dimensions raise questions. The chambers measure 12 feet in diameter, far larger than necessary for the hydraulic system, which could function with 6-foot tanks. The drawing shows only the upper portion modified, with new iron lining, pipe connections and access hatches. The lower portion, perhaps 20 feet of depth, remains as found, lined with original stone construction, presumed earlier foundation work. I searched for records of earlier structures. The Thames Port Authority maps from 1850 show wharves, nothing substantial enough to require 40-foot foundation shafts. The Geological Survey from 1882 mentions no subsurface structures. Yet when excavation began in 1886, workers found chambers already in place, deep enough and sound enough to support major infrastructure. The pattern suggests layers. Tower Bridge's visible hydraulic system represents Victorian engineering. Beneath it, literally supporting it, lies older construction, chambers built for some other purpose, encountered during excavation, adapted rather than removed. Researchers examining what they classify as Tartarian infrastructure note this layering. Victorian construction was built atop, around and integrated with earlier networks, systems that provided foundations, drainage and pressure management without acknowledgement in modern engineering records. The hydraulic manual appendix offers minimal insight: existing foundation voids. The word existing does heavy work, acknowledging presence while avoiding origin. Tower Bridge operates as designed, its hydraulic bascules rising and falling on schedule. Beneath the machinery, in chambers no tourist sees, the layered history remains: older stone supporting newer iron, questions sealed beneath function. Dom Luis Vincent Bridge in Porto, completed in 1886, spans the Douro River with an iron arch, engineering influenced by Gustave Eiffel and executed by his student Théophile Seyrig. The construction photographs, archived at the Porto Municipal Historical Archive, document the assembly process. Photograph 31 shows the southern pier during foundation work, dated April 1884. The base of the pier is exposed, awaiting iron superstructure installation, and clearly visible were conduit openings that predated any ironwork. The photograph captures 3 conduit mouths, each roughly 10 inches in diameter, positioned at the base of the pier approximately 2 meters above the waterline. They are finished, with smooth stone surrounds, no rough excavation, and no temporary bracing. They existed before construction began. The photograph caption reads, "Pier foundation prepared for ironwork assembly." It leaves the conduits unexplained. I cross-referenced the construction specifications. Engineer Theophile Seyrig's detailed plans show pier foundations but no conduits. His engineering calculations account for wind load, thermal expansion, and traffic weight. Nothing about water channels at the pier base. Yet there they are, photographed in April 1884, 2 years before bridge completion. The pattern echoes discoveries elsewhere, infrastructure components found during construction, incorporated into new designs, and never explained in engineering documents. The Dom Luisto Bridge was built atop something else, or alongside it, using foundations that contained features the iron bridge did not require. Seyrig designed iron to span the gorge. Someone else, sometime earlier, designed stone to manage water through foundations that would eventually support that iron. The Tartarian infrastructure hypothesis addresses this layering. Researchers examining what they classify as Tartarian base networks note the pattern of stone foundations with integrated hydraulic systems later used as platforms for modern structures. The modern structure gets documented with detailed plans, construction photographs, and engineering specifications. The base network simply exists, undated and unexplained. The bridge opened in October 1886. Traffic crossed the upper deck, and pedestrians used the lower level. The conduits at the pier base presumably still flow, remain sealed, or serve whatever function they were designed for. Photograph 31 preserves the moment before ignorance became permanent, when the evidence was visible, photographed, and then buried beneath iron construction and a century of traffic. The image shows the question clearly. Why design iron atop an unseen system? The Stone Arch Bridge in Minneapolis, completed in 1883, carried Great Northern Railway traffic across the Mississippi River. James J. Hill's railroad company documented everything: survey maps, engineering calculations, construction costs. The blueprint collection at the Minnesota Historical Society shows foundation details drawn with the precision typical of corporate engineering, every stone course numbered, every pier dimension specified, every structural element accounted for. Blueprint sheet 14 shows the pier-based design. In the foundation cross-section, it indicates water passages, not drainage channels running down and out. Horizontal passages run through the pier base, parallel to the river flow. The notation states water passages per standard practice, 8-inch diameter ceramic pipe. Standard practice for what? Railway bridges do not require horizontal water channels through their foundations. The passages serve no apparent function related to rail traffic. They do not drain the roadbed, the bridge carries trains, not storm runoff. They do not provide foundation inspection access, they are too small, and they are filled with ceramic pipe, not left as open tunnels. They simply exist, specified in the blueprints as if their presence required no justification. The dimensions match the pattern I had traced across continents: 8-inch diameter, ceramic pipe, spacing at regular intervals through the pier bases, the same specifications appearing in London, Paris, St. Petersburg, New York, Porto, and now Minneapolis. The Mississippi River, carrying spring snowmelt from Minnesota forests, received the same subsurface treatment as the Thames, the Seine, the Neva, the East River, the Douro. Why repeat a system that serves no documented rail transport purpose? The blueprint offers no explanation. Hill's company built for efficiency, no wasted material, no unnecessary labor, yet they installed ceramic pipes through every pier foundation, following specifications that appear nowhere in American railway engineering guides, but match exactly the European bridge patterns I had documented. The global consistency defies Victorian-era communication limitations. In 1883, bridge engineers in Minnesota had limited access to European foundation details. Technical journals published general principles, not specific dimensions for subsurface drainage. Yet somehow, Minneapolis received the same 8-inch ceramic pipe specifications used in bridges thousands of miles away, built decades earlier in different geologic conditions. Researchers examining what they identify as Tartarian infrastructure patterns note this global signature: identical systems appearing across continents before international engineering standardization, suggesting not parallel development but inherited practice, specifications copied from some common source that predates modern engineering documentation. The Stone Arch Bridge still stands, carrying pedestrians and cyclists where trains once ran. Beneath the repurposed deck, in foundations 140 years old, the ceramic pipes remain, functional or sealed, acknowledged or forgotten, installed for reasons the blueprints never quite explained. Hill's notation was factual and final, per standard practice. But whose practice and standard since when? I returned to Westminster Bridge on a cold afternoon in November, armed with the 1930s maintenance note and a century of accumulated questions. The bridge carries traffic as it has for 150 years: buses, taxis, pedestrians crossing between Westminster and Lambeth. Nothing visible suggests the sealed conduits beneath the cutwaters, the pressure chambers documented and filled with concrete, the hydraulic systems removed without explanation. Standing at the southern approach, I could see where the 1858 cofferdam photograph was taken. The stretch of riverbank now buried beneath embankment construction, the edge of the Thames pushed back by Bazalgette's Victorian engineering. Beneath that embankment, the 40-metre conduit grid, ceramic pipes laid in 1864 following patterns that predated the construction timeline. Beneath the bridge itself, the filled chambers, the sealed channels, the infrastructure removed during renovations that official construction records never mentioned installing. The pattern traced across 13 bridges, 6 countries, 5 decades of construction. From Westminster to Brooklyn, from London to Minneapolis, bridges built by different engineers in different decades using different materials, all containing the same subsurface signatures. 8-inch conduits, 40-metre spacing, pressure chambers in pier bases, hydraulic valves at depths requiring no surface access. Systems discovered during renovations, documented briefly, then sealed or removed without investigation. The Tartarian hypothesis persists because the evidence accumulates rather than resolves. Old maps labelled vast territories as Tartary, regions spanning Europe and Asia, containing thousands of structures now attributed to various local civilizations. Modern researchers examining infrastructure in these regions note patterns such as oversized foundations, pressure-managed waterworks, hydraulic systems built before documented engineering knowledge could explain their sophistication. Bridges become case studies in this larger question, not whether Tartaria existed. Maps prove it was at minimum a geographic designation, but whether the infrastructure attributed to Victorian engineers might have deeper roots, systems inherited rather than invented, repurposed rather than originally built. I photographed the bridge from the embankment. The image shows granite piers, iron railings, ornamental lamp standards, pure Victorian industrial achievement. What it does not show are the filled conduits beneath the cutwaters, the sealed chambers in the foundations, the hydraulic systems that maintenance crews discovered and destroyed without recording their purpose. Those elements exist only in renovation notes, archived blueprints, scattered photographs taken during construction before concealment became permanent. The maintenance note from 1934 remained factual and troubling. Filled conduits beneath cutwaters. The word filled implies they were once open, once functional. The absence of any installation record implies they predated the documented construction or existed outside official engineering documentation. Filled, sealed, removed, the consistent response across bridges worldwide when renovation crews encountered systems they could not explain. What remains beneath bridges we think we understand? The question has no definitive answer, only accumulating evidence that Victorian engineers built atop, around, and integrated with infrastructure whose origins they never recorded. The bridges stand, traffic crosses, and beneath the documented construction in foundations we rarely examine. The sealed chambers wait, silent remnants of engineering knowledge that renovation records classify simply as obsolete, without ever explaining to whom, or since when, or what was lost when concrete filled the spaces that photographs briefly revealed.